Hey, everybody. Thank you so much for coming out to our talk. We're really excited to be here today. This trip has been a lot of firsts for us. This is our first time in Japan and in Tokyo, and this has been a really amazing experience.
There's having trouble hearing you.
Okay. Right. There we go.
Too tall.
Of course. Thank you. Where was I? Right. So this is going to be the first time that we actually get to come out in the open and talk about all this cool work that we've been doing with the OMR runtime framework. So today we want to take you through our work with garbage collection and OMR and Ruby. So I'm Robert Young, and this incredibly handsome man beside me is Craig Lehmann, and we're two software developers from Ottawa, Canada. We're members of the IBM Runtime Technologies organization. It's an international team, and it's responsible for all of the different language runtime offerings that we make available as IBM to our clients. Our Ottawa lab in particular is known for our work on the J9 Java virtual machine. So our team at the J9 Labs has been in language runtime development for over 20 years. We come from a Smalltalk heritage, and our first IBM product, Visual Age Smalltalk, was first released in 1988. In 1993, we released our first version of the J9 Java virtual machine, and it was created from the same core technologies that we had originally developed for our Smalltalk VM. Since its release, J9 has seen hundreds of person-years of active development. So today we're excited to talk about our new project and the future of our technology, OMR. OMR is an open source toolkit for language runtime development. It's derived from the source code of our production J9 virtual machine runtime, and we're distributing it as a C++ framework open sourced under the EPL. So this is a mile-high view of the architecture of a typical language runtime. And the core idea of OMR is that there's so much of a language runtime that can be shared across different language implementations. So as a toolkit, we're including technology for just-in-time compilation, garbage collection, our portability layer, which is going to get you running on all kinds of really crazy platforms, and our diagnostic and profiling utilities. So the core idea here is that OMR can be this shared backbone between many language runtimes. And with shared development, an improvement to one language could mean an improvement to all. We're currently using it in production code. So this is a code base that has been battle tested and shipped in J9 for years. And in its current form as OMR, it's actively being shipped in our Java 8 SDK. We also have proof of concept integration with Ruby, CPython, and SOM, which is a Smalltalk implementation. We're really interested in bringing OMR to all these different languages because we support them on the cloud, and we want to make these languages as powerful as possible for our clients. But of course, this is a Ruby talk, so we want to talk about OMR and Ruby. So I'm going to hand it off to Craig, and he's going to talk about how we got started bringing our garbage collection technology to Ruby.
Thanks, Rob. So we didn't want to just come out and say, use our great framework. We wanted to actually prove that OMR added value to languages outside the JVM. And we felt that Ruby was a great fit for that. So today we're going to talk about our work integrating OMR's garbage collection framework into Ruby. Along the way, we hit some roadblocks, some snags, but we also had some really awesome success. So we're going to start right from the beginning, where we knew nothing about the internals of CRuby. So, all right, so step one. How do we put the OMR GC into Ruby? Well, in order to do this, we needed to know what was going on under the hood of the VM. Unfortunately, we didn't know anything when we started. So we did what anyone would do in this situation. We turned to our savior, Google, and we searched for answers. How does garbage collection work in Ruby? Through this, we actually found in 2013, you could buy a GC book. Unfortunately, we don't speak Japanese yet, so we were left with reading the source code. So we opened up gc.c, the main C file associated with garbage collection in the Ruby interpreter, and we noticed something interesting at the top of the file in the header. The file was created in 1993. So, Rob, let's think back to us in 1993. As you can see, we weren't exactly garbage collection developers. But in all seriousness, C-Ruby has been in active development for over 20 years. During this time, it's built up a fantastic worldwide community, as is evident by all the great people here. Ruby as a language has evolved to become more expressive and powerful over the years. Over those years of development, MRI has a lot of history and complexity in its design. So after diving more into reading the source, here are some of the things that we noticed. The Ruby internals are set up to directly use object pointers. The GC needs to be able to mark these pointers, which is done by conservatively scanning the stack and marking them if they look like valid objects. This allows C extensions to directly use object pointers. However, as a result, objects in Ruby cannot move. The next thing we notice is that objects in Ruby are a fixed size of 40 bytes. Obviously, Ruby objects must be larger than that if you have a big string or array. So Ruby needs a strategy to deal with these larger objects. It does this by mallocing any additional space needed for large objects. Now, the advantage of this is that the managed heap has no direct memory fragmentation, and it makes conservative marking easy. There are some downsides, though. Malloc and free are slow. Sweep slows down if you need to free these backing buffers associated with the malloc space on objects. You may also still have fragmentation issues in the malloc space. It's sort of a black box implementation. Finally, allocating buffers away from your objects means that you could have cache locality issues. Right. But Ruby has an incremental GC, and it interleaves marking and sweeping with your executing Ruby application. As I just mentioned, in C Ruby, sweep times are longer because they need to clean up that malloc memory associated with objects. But the incremental GC alleviates those potentially long GC pause times by sweeping on demand. Okay, so now we have a better understanding of GC internals. Let's talk about what we actually did to put Omar's GC into Ruby. We started out with these goals in mind. We wanted to make allocations faster, improve GC time. We wanted to improve the mutator performance. Mutator is what we call application, so improve the application performance of your Ruby application. And above all, we wanted to maintain 100% compatibility. So this means no C extension API changes. You can pass any test, anything you can run on Ruby today, you can run with Omar's GC in Ruby. Okay, so let's start small. Let's make it work. Let's get a simple, single-threaded mark sweep implementation of our GC into Ruby. These are some examples of code changes you need to make. In places where you kick off a Ruby GC, you instead kick off an Omar GC. Where you'd allocate a Ruby object, you instead use Omar's allocator to get that memory. With a few more hookup points like this, you've almost plugged in the Omar GC. However, Omar's heap is not slot-oriented like Ruby's, and because of this, we needed a way to support conservative collection. So we added an object map to indicate the beginning of valid objects. All right. So at this point, we have a single-threaded mark sweep implementation of our GC in Ruby, but let's make it parallel. Okay. As we all know, parallel programming is hard, and sharing a workload between threads is hard. But the code to do this efficiently already exists in OMR. OMR exposes an easy-to-use and portable API for parallelism and atomics. The Omar GC has features like advanced work-sharing algorithms, highly parallelized internal operations, worker thread pooling, and task synchronization. So in order to split up marking and make that parallelized, we started with the roots. Any root that was too big to be scanned in a single thread was broken up into smaller work units. After that point, the remainder of the marking phase is handled by Omar's GC, and it's marked efficiently in parallel. Now, to support this, we had to make some changes to internal GC APIs in Ruby. We had to pass around a thread context. For C extensions, we store that thread context in thread local storage, and this allows us to have parallelized marking without breaking anything in the C extensions. All right, so the next step following marking is your sweep phase in GC. Some objects, such as C extension objects, needed to be swept together to protect the C API. However, we were able to sweep simple types like strings and array in parallel with each other. Additionally, when you have various objects within Ruby, they may be associated with or referenced from various internal VM data structures. When that object dies, you need to update that data structure and remove the reference from it. We pulled that work out of the on-demand format and do it entirely in parallel with the rest of the sweep work. Okay, so hey, it works. At this point, we now have a parallel mark sweep GC in Ruby. Not only that, but with Omar, you get a couple of cool tools. So this is a tool that comes with our GC for free. It's Garbage Collection Memory Visualizer, or GCMV. It allows you to visualize information like the size of your heap, the amount of free space, GC pause times, that sort of stuff. And beyond just giving you the direct analytics, it also will offer profiling recommendations to help you optimize the performance of your GC. Another tool that will be available to use with Omar is Health Center. Health Center attaches to a running application to provide you with information in real time. So this is the GC view of Health Center. It's very similar to what we just showed in the previous slide. It can show all the same information, but it's from a running application. Another popular component of Health Center is method profiling. So with a little bit of extra work and some glue in the VM, we added method profiling to Ruby. This allows you to do things like show the call chain of each sampled method and sort methods by accumulated proportion of time. So this picture shows a running Rails application in Health Center. Essentially, I guess the key takeaway is that these tools are currently used in production for Java, and they'll be available to be used by any runtime consuming Omar. Okay, so let's keep digging into Ruby. Rob's going to talk about how we made Omar's GC in Ruby even faster.
So I guess our primary goal here was to make your application faster. So our first stop was to look at object allocations. We wanted to make your mutator faster and get those objects allocated a little bit more quickly. So we brought from OMR the concept of thread local heaps. And essentially what we do here is we take a big contiguous region of the heap and we give a thread exclusive ownership over that region so it can do whatever it wants with it. That's going to let the thread allocate without any kind of global synchronization or without taking a lock. As well, objects that are allocated together are used together. And if they're all coming out of this same physical region of memory, you're going to experience great cache locality in your mutator's execution. Of course, when we use TLHs, we're only really looking at big free spaces of memory. So we become susceptible to heap fragmentation if free memory is very small, in small pieces and chunks. So the idea here is that inside of a TLH, a thread is going to be allocating its objects from the left towards the right. And by giving a thread exclusive ownership over this region, that thread is going to be able to get away with tracking very little global state. So as we allocate left to right, we can see exactly how little of state we're really tracking. It's just this next allocation pointer and the remainder of the free space in the heap. It's a technique that's known as bump allocation, and it's extremely fast and extremely inlineable because it's so simple. And we've worked really hard to really pare down our allocations and make them fast and inlineable to get your mutator running faster. But we wanted to continue to make things a little bit more quick. So we did some profiling. And we noticed that malloc and free, as we've already said, are extremely expensive because almost every single object that's allocated in your program, it has some off-heap memory that's associated with it. And that has to be mallocked, which happens along the critical path of your program. And that's slow. But maybe even more critically, in the garbage collector, when that object dies, that memory has to be freed. So for every single dying object, we're doing finalization and we're freeing off-heap native memory, and that's extremely expensive for us. So the idea here is to replace malloc and free with something that better suits our needs. We have to remember that malloc and free are suffering from the same kinds of challenges that we, as VM memory management and like garbage collection developers are facing. So things like concurrency and fragmentation and cache locality. But the malloc and free API is extremely restrictive in what it can do, and the implementation is a black box, so we have no control over what it can do. Our idea here is to take VM-specific knowledge to build a new kind of allocator that better suits and fits the needs of the Ruby virtual machine. So we introduced a new built-in type to Ruby, and we called it the Omar buffer. The Omar buffer is the only variable-sized object that's allocated on the Ruby heap. And the idea is that it consists of a header and a data portion that can be used in place of things that were traditionally mallocked. And so in large part in the VM, we've transparently replaced mallocked buffers with these on-heap Omar buffer objects. And we're transparently using pointers to the data segments of these objects instead of the buffers traditionally off-heap. So we've used Omar buffers to move that mallocked and off-heap data associated with built-in types onto the heap. So they're using that same really fast object allocation path that we've introduced. And they're going to experience great cache locality because they're allocated often right beside that parent object that they're associated with. As long as the buffer is reachable from either a root, like the stack, or a parent object, it remains alive and it can be used. But the best part of this is they don't need to be freed. So when they become unusable, they're automatically collected by the garbage collector. And so by moving data onto the heap, we've eliminated the need to free all of this off-heap native memory. And since we've already moved so much of object finalization out of the act of sweeping individual objects and into parallel work units, we've actually almost eliminated the remaining work associated with sweeping objects. So, of course, we wanted to add new API to help get C extensions onto the heap to make things like Nokogiri a little bit faster. So we've added this new flag to the OurData API, and what that gets you is an implicit allocation of your traditionally off-heap memory on the heap. And if there's no other work, for example, you're traditionally using default free, you're able to actually delete your free method, and this is going to allow the collector to elide any kind of additional work that would happen during the sweeping of your C extension objects. It respects the same kinds of semantics that the traditional OurData API has always sort of offered, in that the lifetime of your memory is associated with the lifetime of the OurData. So this is going to make it extremely easy to use, and for simple types, just add the flag, and for free, you're going to get better cache locality, faster allocations, and shorter GC pause times. So what we're seeing is that Omar buffers has helped us to eliminate object free, give us faster allocations in the mutator and better cache locality, and this is overall going to improve the execution of your program. Of course, we're dealing with some issues with the introduction of Omar buffers. Adding variable-sized objects to the heap is introducing heap fragmentation, which is where some regions of memory become unusable. We've had to modify the way that conservative collection is working so that we can keep these Omar buffers alive because we're using them instead of off-heap memory, things that traditionally weren't marked. And as well, we've run into some really interesting issues with concurrency in the MRI internals. So as it turns out, MRI might actually do some kinds of internal operations without holding the GVL. You're going to see this with typically long I/O operations, so things like reading from a socket into a Ruby string object. Operations like this will assign into these slots and create, resize, or even free the native off-heap memory associated with Ruby objects. But now with Omar buffers, this memory is on heap. And so we've had to introduce a new finer-grained locking mechanism that's more permissive than the GVL has traditionally been. And so this is going to let us manage and allocate our Omar buffers from background tasks. And so with this, we're seeing some pretty cool things like truly parallel allocations and things like directing and triggering garbage collections from background threads without holding the GVL. So at this point, what we're seeing is meaningful, real object graph mutation and the transformation of the heap in an actual multi-threaded environment. And so we sort of see this maybe as a first step towards a multi-threaded Ruby implementation. By plugging in our garbage collector, we're seeing overall an 8% better throughput on Is Ruby Fast Yet, which is a stress test for Rails. And we're seeing GC overhead being reduced from about 8% to 3% with our collector. But of course, over our development of Omar and Ruby, we've sort of done a lot of experimentations, and so we have a lot of more work that's kind of ongoing, and I'd like to take a little bit of time to actually talk about that. We're experimenting with reintroducing a non-copying generational GC into Ruby with Omar. This is not something that has been traditionally supported in our garbage collection framework. What this is going to do is help alleviate the CPU time costs of the marking phase of a garbage collection. But since we're already concerned with heap fragmentation issues, we want to reclaim the maximum amount of memory possible in a GC cycle. As well, because we're making different guarantees about the layout of the heap and object alignment, we're seeing a high cost of the implementation of bitmaps and the implementation of generational garbage collection with Omar. We introduced a segregated heap into Ruby. And so this is where we've divided the heap into different regions, each one of a different fixed size. And this is going to help us make certain guarantees about the maximum amount of heap fragmentation that can occur on the heap. This is extremely useful for very long-running Ruby processes. We're experimenting with bringing more OMR features into the OMR framework and into Ruby. So we're adding our concurrent garbage collector into MRI. So this is much like the Ruby incremental garbage collector in that we're interleaving the marking phase with mutator execution. However, we're also offloading a lot of that marking work to background threads so that we can do marking outside of the critical path of your application. This scheme would still use our same stop the world but parallel sweeping phase. Okay, so now I'm going to hand it back to Craig, and he's going to talk a little bit about what's next for Omar and Ruby.
All right, thanks, Rob. Okay, so in addition to the ongoing experimentation Rob just mentioned, there's also some more GC technology that will be moved into OMR soon. Balanced GC algorithm is a GC policy that allows you to take advantage of very large heaps in your application. So think a heap over 28 gigabytes. Another algorithm that will be coming soon is a semi-space copying generational collector. So similar to the generational collector in Ruby now, but this would actually move objects into different portions of the heap. The advantage of this is it improves cache locality and just decreases your GC pause time overall even more. But the Ruby internals right now aren't quite set up to allow that. Objects can't move within Ruby, as I mentioned before, but potentially in the future, there could be some things rewritten that may allow objects to move. If that happens, there's essentially going to be a really fast copying collector already ready to go. Okay, so what's next for Omar? We've done a lot of work today and in the past to talk about Omar's GC and how it can be used in Ruby. We've increased performance, we've added features, and we want to make it clear that we're not interested in forking Ruby. We don't want IBM version of Ruby. We want to contribute this work that's ongoing directly to C Ruby. We want feedback from the people here at the conference I think you guys are really the true Ruby experts, so we want to hear from you and to hear what you think about the project. This weekend, we're releasing a technology preview for RubyKaigi. This will contain all of the GC changes we talked about today, albeit not the experimentation that's still ongoing. And if you caught Matthew's talk on Friday, it will also contain the JIT work that he's been working hard on. So this won't actually have the OMR directories available, but we hope the OMR work will be open source very soon. So please go to this link, check it out, and let us know what you think. Okay, so this is a slide. A lot of you have seen this, I'm sure, by now. But it's from a recent presentation at RubyConf, where Mats was talking about assistance in making Ruby faster. So as Mats mentioned on his keynote in Friday, IBM is looking to contribute directly to C Ruby. We hope that the Ruby community is interested in the work that we've done. We want to help increase performance in Ruby. We're continuing to work on OMR, and we're excited to build upon and do even better than what we've shown today. Okay, so this sort of wraps up the talk. Thank you. Arigato. If you want to get in touch with us, my name's Craig. This was Rob. You can email or message us on Twitter. And we also have our GC architect for the Omar project, Charlie. Feel free to get in touch with him if you have questions. Mark is the Omar project lead, and John is the CTO for IBM Runtimes. So with that, I'm assuming we have time for questions, but I'm not sure. Yes. Certainly. Yep.
You actually still have 10 more minutes. So any questions from the audience? Sasada-san.
Thank you for great presentation. My question is, I can't understand what is the finished work and what is the future work. So you mentioned many techniques. So what is the finished one? And your implementation is so complete compatible or not?
Okay, so
my question is, what is the current status?
What's in the tech preview kind of thing. So when we went through, we sort of showed the performance stuff here, and before that we were talking about all the work with Omar Buffers. At this point, that's actually available. The ongoing experiments from this point on, those are something we're doing right now, and we do hope to make that available soon and post some numbers about what happens with this work as well.
What is the benchmark? So you show the benchmark results. What's the type of benchmark you show?
Okay, so it's a Rails test.
Rails test?
Yeah, measures the amount of requests, I believe, to a Rails.
So this is a second or percentage?
It's percentage.
Percentage, okay.
Yeah, 8% better, more requests received.
Compare with what? Sorry, compare with what? So 100 is what?
Right, so on the left, there's the Ruby implementation with Omar. Mm-hmm. On the right is stock Ruby. So sort of compared between the two, it's a little bit hard to see, but it's 122 requests with 2.2 Omar, 112 with 2.2.3 Ruby.
I see.
Okay.
Okay, so it is, you say that it's complete compatible with MRI?
Yes, complete compatibility, nothing's broken.
Okay, thank you.
Yep.
On the test, is there any implicit memory use on the thread local memory and using separated memories for different sizes of the objects?
Okay, so we're talking about memory usage of the
Yes.
runtime during the execution of the test. So our binary, of course, is a little bit larger. Our heap was hammered at 1 gigabyte, and we achieved a similar resident set size of memory compared to 2.2.3 by just through experimentation and tuning. So this is with comparable sizes of memory. Does that make sense? Okay. Sorry.
I have two questions, if that's okay.
Okay.
How expensive are finalizers in the OMR GC?
So when we talk about object finalization, we're talking about the sweeping of objects, which is not the same as the Ruby feature of finalizers.
Sure.
Finalizers in OMR are not particularly expensive.
And my other question is, you talked about your fine-grained locks.
Right.
Are the fine-grained locks just in the allocator, or like where did you move the locks to?
Okay. This was finer grain locks in reference to into VM access. Okay.
I think so.
Right,
You
okay,
had it.
sorry, right, okay.
You talked about it in reference to object allocation.
Right. So these, the idea here is that any any thread that's doing any kind of meaningful heap mutation or execution is holding access to the virtual machine. And then when we need to bring the virtual machine down to perform a garbage collection, that directing Ruby thread is going to obtain exclusive. And so then we're going to wait for all other threads to give up their access and take a nap, and we'll execute our GC. So we're using VM access in addition to interpreter execution for guarding heap mutation.
Okay. You said that it's possible with your fine-grained locks that there is mutations happening on multiple threads, or that you're doing object allocation on multiple threads at the same time?
Yep. So it's instead of being an exclusive setup where only one thread can hold it at a time, multiple threads have access, but then to perform certain critical operations, we'll bring it down to exclusive access.
Okay. What section is the fine-grained locks protecting? So
So the asynchronous call.
Okay, in the asynchronous call, we're dealing with the assignments, write barriers, and allocation. It's also guarding the entire execution of the mutator while holding the GVL.
Any other question?
Thank you for the interesting presentation. Regarding the benchmark you showed, which portion of your JC techniques contribute to the increasing performance? For example, like memory allocation becomes faster, or the JC stop times becomes shorter, or those kind of things.
Well, we're seeing better mutator execution. Primarily, we've reduced dramatically the amount of cache misses that happen, and this has contributed a lot to that throughput that we're seeing. As well, total GC overhead being reduced from 8% to 3%, so that's about 5% of that improvement that we're seeing here.
Thank you. And in case of that GC time, how many threads were you running?
4.
Okay, thank you.
So you may have explained, but so how did you implement that your OMR version of Ruby? Is it so based on the existing CRuby implementation and just replace the C part, or did you re-implement the whole Ruby interpreter yourself?
Okay, so one of our major goals was to modify as little as possible. So this was based off of MRI 2.2.3, and we've changed none of the interpreter. We've just sort of plugged in where we had to our allocation pass and our garbage collection kickoff logic, while touching as little else as possible.
Okay, thank you.
Is everyone all right? Okay, so thank you for the great session. Guys from IBM, thank you very much.